So some of the components or processes that it deals with, so it has to deal with all the temperate zone processes as well as the cold ones that we have in Western Canada. And I'll go through them very quickly. So blowing snow, it's a two-phase flow, saltation and suspension of blowing snow particles. Importantly, these particles sublimate very quickly as they travel across the prairies. So blowing snow particle half-life, some people have estimated it at about a half-life distance of about 3 kilometers. And so that's important when you're designing shelter belts, things like that, for filling dugouts. It also means that we can move water uphill in and out of watersheds, and it means that we can manage it by managing tall stubble. So when we look at BMPs, management of blowing snow redistribution is very important. And it's something that we worked on a number of years ago, saying that, well, if we left tall stubble around the prairies, we could trap a lot of the snow, hold it in place, reduce the sublimation losses. But the problem is, if you do that without looking at the soil, you're going to generate lots of runoff and some erosion, and that may not be the objective one has in mind. So you need to deal with the soils as well. And actually this is Saskatchewan on the weekend, so a bit of blowing snow in there. And we can go to St. Denis, Saskatchewan, and model blowing snow as over a 6-meter grid. I'll show you a simulation from 250,000 grid cells run over a winter in the hummocky landscape of St. Denis. And from this, we can produce snow water equivalent maps that are reasonably accurate. You can see the grid road network and the snow in the ditches, and then the snow around the sloughs and the tree rings around them, and then the scoured hilltops in that hummocky terrain. So this has been quite valuable for us in trying to estimate the runoff and the filling of these sloughs and their desiccation during droughts. Then melting the snow, one thing that was learned many years ago is that temperature index methods tend to fail on the prairies because net radiation is about 90% of the melt energy for snow melt here. So it's not the Pacific Northwest, you can't use the temperature index reliably. Fortunately, there are methods to estimate the energy balance for snow melt, and so we can do it using temperature, humidity, and wind speed, even without direct radiation measurements. And so those exist for us. And finally, the soils. So Don Gray, Don Norum, others at the University of Saskatchewan spent many years working on the properties of infiltration into frozen ground. And it's an incredibly complex, difficult problem. I won't go into in much detail, other than the infiltration rate is not governed only by the hydraulic properties of the soil. It's governed by the energy balance in the soil. So the heat and mass transfer as the infiltrating wave moves into the frozen ground, it's of course refreezing, which is releasing large amounts of latent heat. We now have solid components in the soil, air-filled voids, water-filled voids, and ice-filled voids. And there's also swelling and very complex tension relationships, and some chemistry involved, as the ice will exclude some of the salts, and so that some of that liquid water tends to be very briny. So all kinds of things going on in there. One thing Don Gray did years ago was to simplify it and say, well, we can break soils into 3 classes. One which would be an infiltrated class, where there are large macropores and cracks. Essentially, the seasonal snowpack will completely infiltrate those soils. So that can happen if you're subsoiling it, ripping it. It can happen where there are natural cracks which form. Swelling clays are a good example for that. It can, and back in the 80s they weren't thinking of this so much, but it can also happen under minimum tillage, where natural macropores start forming in the soils and water can enter. More often, though, we're in this limited case where the infiltration is a function not only of the snow water equivalent, but of the degree of saturation in the soil, and you can usually get that from measuring the fall moisture content in the soil. And then we also have restricted case where nothing gets in, so that can happen if the soil is saturated when it freezes. It can happen also due to midwinter melting, which will put an ice layer on top of the soil. So you could have a dry soil with an ice layer capping over the top. You're still going to be in that infiltrated, restricted infiltration case, which means all the snowpack runs off. And that's the one for flooding that we always watch for as being a very, very dangerous situation. It's amazing the effect of frozen ground on the runoff. This is just a model simulation for the Bad Lake area. It's some year in the 1970s. What we did in here, we used a frozen soil algorithm, and this is the runoff with with an unfrozen soil algorithm. So we falsified the model now, and in this case it was using the National Weather Service runoff forecast system, modeled it as if it was unfrozen. There's no runoff, and so that tells us some of the hydrological importance of that frozen state. Gray's very simple model can be expressed like this. You've got the restricted case where very little spring infiltration occurs no matter what the snow water equivalent. You have the limited case where essentially everything infiltrates. But most often we have this case in here where the amount of infiltration is controlled by the snowpack that's available to melt and the degree of saturation of those soils. And so a lot of our modeling is saying, well, from the fall state, can we look at the overwinter changes to soil moisture and then use that to estimate how much might infiltrate in the spring. And so when you put it into a model, you would take snowmelt water and apportion it based on the classification of the soil state, and then it's either infiltrating into the soils or forming runoff. Okay, so we'll go back to Bad Lake and some of the data from there. So it's Bad Lake is in it's not near anywhere right now. It's sort of south of Rosetown, Saskatchewan. If you've driven between Saskatoon and Calgary and passed through the town of Fisk, it would be a few kilometers south of there. So it's in an upland moraine. It's internally drained, and there's an 11 square kilometer tributary, Creighton tributary, where we've had very detailed measurements and we're able to do some model testing and evaluation there. And the thing is, we can take Creighton tributary and take that as a virtual prairie basin and say, well, this is how it behaved in the 1970s. How would it behave now with all the changes to agriculture that have occurred? And so this is putting together a model from using CRIM for Creighton tributary and looking at the water balance as it was in the early 1970s. So in that case, fallow fields, stubble fields into a coulee, and the coulee into the stream. Pretty simple prairie system. At that time, it was about 30% summer fallow, and the grassland coulee occupies 15% of the watershed. And so they're all getting the same snowfall and the same rainfall amounts, the fallow, the stubble, and the coulee parts. But there's a lot of snow blowing off the fallow. Some blows to the stubble, then it gets passed onto the coulee. So we get these snowdrifts in the coulee, which really make that the important part of the watershed for runoff generation, not so much the fallow and stubble fields. And then the runoff generation from those being fairly small, the runoff from the coulee being quite large. And so we can take that system and say, all right, let's take it forward to the current time with some hypotheses. One is that we're going to get rid of summer fallow completely, so we're going to leave stubble. I think we left it at 25 centimeters in the simulation. We're now going to have much drier soils in the fall because of continuous cropping, and so we don't have the high soil moisture in the fallow. And we're also going to allow some macropore development because of the lack of tillage in these soils. And we get now we have a stubble coulee system and much less blowing snow, but remarkable changes. So holding the climate the same here, the runoff has dropped off about 25-30%. The infiltration has increased 40% over time. Snowmelt has increased a bit because we have reduced blowing snow sublimation losses. Those have now decreased 35%. And there's a slightly smaller amount of evaporation in this case, but probably not that important. The main thing that's going on here is a large increase in infiltration, a large decrease in runoff in the system. And so the sort of the physics that are incorporated in this model suggests that, okay, the adoption of some of these practices were very effective at keeping the snowmelt water in the soil and reducing runoff from the watershed, and basically we focus the system now as an agricultural water use system, for better or for worse. If you're a waterfall, dependent on water to fill up a slough downstream of this. This is not so good. If you're trying to use this to fill a farm dugout, not so good. But if you're trying to grow crops on an annual basis, it can be very good. So I thought I'd talk a bit about drought rather than flooding, because we've had a lot of flooding now, so we're probably due for a drought this year, so it's time to start thinking about it. So I'm going to dig up some old drought things and jump into that. So and many definitions of drought. Agricultural drought, of course, is largely based on soil moisture characteristics. It's very strong atmospheric feedbacks to that. As soon as the climate goes into a climatic drought, we're pretty well into an agricultural drought as soon as summer hits. It might start in winter, we just wait for the end of winter and then, okay, it's drought. And so that's largely controlled by soil moisture. Hydrological drought is a little bit different, and it takes much longer for it to develop because of the amount of water storage on the prairie. So if we're going from a wet situation where we have lots of water stored in deep soil moisture and perhaps in sloughs, those sloughs in particular can take several years to completely dry out. So we don't immediately go into hydrological drought, and we don't immediately recover hydrologically when drought ends. We have to fill up all that storage again. But generally, the agricultural drought, the plants are pretty good at getting that water first when it does come back. And so you see a fairly strong drop in snow accumulation, and the grassland, the coulee, there's very little impact on snow accumulation there as we vary the grass height in the coulee, because the snow is accumulating there because it's a topographic depression. It doesn't matter whether it's tall grass or short grass, but it has a very strong effect on stubble, as we go from tall stubble to shorter stubble. And it's presuming that maybe during a drought there's not much stubble left on the field and the crops are short. So what's happening there? Well, the redistribution, you see there's a tremendously strong impact on blowing snow sublimation. It kind of collapses as we drop the precip, and that's because the incidence of blowing snow drops off quite a bit. As we warm up the temperatures, there's also a collapse in sublimation of blowing snow. So in this case, you normally think of evaporation getting higher as things warm up. Blowing snow sublimation becomes lower as things warm up because the snow becomes more cohesive. It's wet and sticky, has a higher critical wind speed for which is required to make it blow around. And so we get almost complete cessation of blowing snow with a little bit of warming in there. As we decrease the vegetation height, we get an increase in blowing snow sublimation because there's less vegetation to trap it. And of course, soil moisture doesn't have any impact on blowing snow sublimation at all. So it gives us some idea what's occurring as what might be happening in drought occurs. Now we keep following the water to look at the snowmelt runoff. This is 80 to 90% of the runoff in this environment over the year. And with the drop in precip by half, we get a complete cessation of any spring runoff from this watershed in there as we go down from 160 to 80 millimeters. And again, with warming, holding the precip constant, but warming from -7 to -2, we also get complete cessation of any snowmelt runoff. So these are quite concerns, and of course, you've all seen droughts, so it makes sense as well. We have but this explains the shut-off mechanism to some degree. There's also a sensitivity to soil moisture. Generally, the fall soil moisture is going to be lower in a drought, and that will cause reduced snowmelt runoff. And very little impact of the change in vegetation heights associated with the drought. So the largely temperature and precip driven, but strongly mediated by soil moisture. And you might call this soil moisture impact a transient impact of the drought. The drought could start in the winter after a wet fall, and we would just have these impacts. But then the subsequent year, now we have a dry fall, we're perhaps be into this system here.